Okay, welcome back to Module 3 of the Model-Based Testing course at Chalmers and Gear. So, in this one, we're going to focus on white box, so-called structural testing, which is a specific testing technique. But first, I will make some additions to Module 2, given your feedback there. You wanted a few more examples of some aspects. We'll look at that first, and this also leads us into testing techniques and testing levels and different testing goals. So it's a good sort of setup. So most of this video will just lead up to white box testing, and then in the coming module we'll go deeper on exactly different techniques and different goals in different types of structural testing. Okay. Let's get started. So a little bit more on software faults, errors, and failures. We talked about these terms the last time. Here's a little bit more detail about that. Just to remind you, software fault is some defect, some bug in the software artifact, typically the source code. The software failure is an external incorrect behavior of a subsystem, a function, or even the whole system of software. Sometimes it's only seen on the outside of the whole thing, but it depends on what you look at as your system. So when you're developing, for example, a failure, you can talk about a failure in some component or function even. The software error in one of these fault error failure chain terminologies is an incorrect internal state. So on this slide, Aman and Offut, which is some colleagues here, they stay with the classical software reliability definition of fault, error, failure. But as I told you last time, an error can also be the human mistake that leads to the fault in some terminology. But the error here is in incorrect internal state. So faults or bugs in software are equivalent to design mistakes in hardware. So software itself doesn't degrade as an artifact, but often we talk about software rot, which is that because of the surrounding environment, that the requirements and the uses of a piece of software will change over time. You can see this as the software stays the same, but it's less adapted to the context. So basically our expectations change, and then that could be seen as a future failure of the software. So to give you a little bit sense of the different terminologies used here. So to take an abstract example from Aman and Offut on this, fault and failure, a patient goes to the doctor and talks about symptoms that they have. And the symptoms are failures. So this is externally visible things that they feel that they are coughing or they have a fever and so on. Now the doctor tries to diagnose the root cause of these symptoms, of these failures of the system. So this is then looking for the actual fault that is causing the failure. And the doctor may have to look for anomalous internal conditions like high blood pressure, irregular heartbeat, bacteria in the bloodstream, and so on. So these would be errors in our world. So this gives a little bit more example. Most medical problems result from external attacks, though, so that's a little bit different here. Or with degradation as we get older, while software faults are there from the start, and they don't really appear because the part itself wears out. It's more because of our expectations could change. So there's a slightly different thing there. To give a concrete example, if we look at this piece of code for counting the number of zeros in an array, we start by setting the count to 0, and then we have a for loop over the elements of the array, and we count how many times this is 0. And here actually there's a fault in here. We should start searching at 0 and not at 1. So when we actually run a test case, which is to give the input an array with a 2 in the first position, a 7, and then a 0, we expect the output to be 1 because there's 1 0 in there, and the actual answer is 1. So we don't see any failure of this piece of software, although there is still an error when we execute it. And the error is that I still only starts from the value 1 and not from 0, which would be the correct behavior on the first iteration. So basically it is not looking at the number 2, which is at the first element of the array here. But another test case, which has the 0 at the start, then followed by the number 2, and then followed by the number 7, then we expect the answer to be 1 because there is one number 0 in the array, but actually we get 0. So in this case, the error is still there, but the error is said to propagate to the result here through the variable count in the program. So there is actually a visible failure on the outside of this unit, code unit here, the function. So in this case, the fault is there in both executions because the fault is there statically in the code. The error depends on the actual execution, so on the actual test case. And for one test case, there is an error is there because that is caused by the fault, the bug in the code, but there is no failure. And in test case 2, it leads to a failure since the error is there and it propagates to the outside and has a visible effect. Hopefully that clarifies things. When it comes to costs of testing, we just mentioned that briefly the last time, that it can be very costly. I mean, depending on which company you are and in which area you work, the cost is sometimes stated to be 25-30%, but it can also be higher, up to 50 is not uncommon. And for some safety critical domains, it can go as high as 60-70%. But what can happen is that people don't realize that there's a big cost when you're not testing also. So poor program managers or people in companies might say testing is too expensive, or even engineers. We can't do it. We have to reduce the cost of testing. And this is understandable because it is one of the most time-consuming activities in software development, and thus it's also one of the more expensive. But to not test can be even more expensive, right? We talked a little bit about it last time, that you can have effects on your brand if there are failures, or if people even die, or there are economic consequences, right? And there are many different studies on this, but basically if you have too little testing effort early on while you're developing, the cost of testing later in the project tends to increase. So this is really a balancing act. How much testing should you do at which point in time during development to minimize the total cost of ensuring a high quality product? So if you plan to do the testing after development, when you've already deployed to customers, this can be very, very prohibitively expensive. So in all projects, you need to find often a trade-off here. So what does this mean? Overall, this trend we talked about last time, that software testing is getting more and more important. There's a lot of research in this area. Companies are understanding how important this is. But some questions come up. What are we trying to do when we test, and what are our different goals? We'll look at a simple maturity model here. So we can look at the maturity of a company or a project, or the people in a project. You can look at testing and debugging and quality at different levels depending on how mature you are. So at level 0, sort of a base level, you don't even see a difference between testing and debugging. It's all kind of seen as all of these things that you have to do to ensure quality. before you release, but you don't have a clear understanding of what are the strengths of the different techniques, how should you trade off between them, and so on. At level 1, the purpose often becomes to show correctness. So your managers or the engineer think that you can actually show that a piece of software is correct by doing certain types of or levels of testing. When you mature enough, you have more experience, and you realize on level 2 that you want to find and avoid the cases where it clearly does not work. So this is different from level 1, because since testing is a dynamic technique and the input space and the output space of the piece of software and the system is huge, we cannot formally prove that it's correct. Okay, we would need to do formal methods that can actually prove things if we were going for level 1, but in practice this is not possible, and especially not with today's technology. So on level 2, you see testing as helping to show that you have high quality, but in particular to weed out problems that you have, so things that doesn't work. Level 3, you have a more mature understanding. You know that you cannot find sort of all cases where it will not work. So the purposes of testing is to be one piece of the puzzle in reducing the total risk of using this software, right? So in all types of engineering processes and methods, there is going to be an ultimate trade-off. So you don't have infinite resources. When you're building a bridge, you have to trade off how strong do you make it compared to what are the most likely use scenarios. And then you often take like a security margin. So you take, let's say, double or 5 times as strong you make the bridge as you think the expected load is going to be. So you're trying to reduce the risk, but you will not be able to have the resources to make it 50 times stronger than it needs to be, right? So there's always going to be these trade-offs in mature engineering processes. And seeing testing as one verification and validation technique, a very important one to help you reduce the risk, is a more mature level of the goals here involved here. On level 4, testing is a mental discipline, so then it sort of permeates the company and the team and the people involved. So you have a mature view of these different levels and goals for testing, and you have, since all people have an understanding of this, you can sort of dynamically do trade-offs. You can have good plans for your testing and quality work early on, but you can also dynamically trade off and increase certain type of testing while maybe waiting with other forms depending on what happens in the project and the timeline, the new input from the customers, and so on. So I've said most of this. At level 0, you believe basically that it's kind of testing is a kind of debugging. So you don't have a good understanding of the fault, error, failure chains and these different terminologies. So this can be, so you're not using testing effectively to build reliable or safe software. And this is unfortunately what the focus is in many computer science programs around the world. It's kind of viewing testing as similar to debugging. It's kind of done a little bit earlier in a sense. So we need to give a more mature view here. On level 1, purpose is to show correctness, as I said, but this is impossible to achieve. What actually do we know if we run our test cases, we run our different methods of showing software is of high quality, but what does it tell us if we get no failures? Do we know that the software is really good? It can be. An alternative explanation is that the tests are not very good, right? So it all depends on the amount of effort you put into your quality work and your testing work. So just reporting to higher level managers or project managers that, oh, we run all the tests, there were no failures. This doesn't really tell you a lot about how high quality the system has, right? So the problem on level 1 is that test engineers don't have strict goals. They don't know when to stop the testing from, right? This is extremely important, that you have criteria for what are you trying to achieve. And those criteria can help you to say, stop. We probably have a good trade-off now. We have a good level in our testing. And they have no formal testing technique, so a lot of the testing on level 1 is basically based only on experience or heuristics for how what we should test and how we should do it. And managers that are supposed to run the quality and testing often are not listened to in the overall project management or at the company level, if most of the company are on level 1. In hardware engineering, this is often a focus on correctness, and there's a risk in some companies that they are stuck on level 1. In level 2, you add the notion of wanting to find problems. So you're actively now using the testing techniques to weed out problems. And so this is a kind of a negative activity. You're trying to find the difficult cases and find failures by doing that. The downside with this is that you have this notion of independent testing or independent testing teams. So you have developers on one side, and they are supposed to be creative and develop the source code, design it, and so on. And then they sort of send the software in its current state over to an independent testing team, and they are supposed to attack and find problems with this. But again, there's a problem what if we don't find anything, and the fact that you've set it up, which in some industries you're required to have an independent testing team, but if you have this type of compartments within your organization, the risk is that you don't get a lot of good communication and knowledge transfer between these groups, so they are not really helping each other. They are sort of against each other on level 2 thinking. One trying to find problems, one trying to add new features and weed out the problems that these find. So you're not seeing collaboration on a good level. So this describes most companies still. I mean, many have, of course, especially with the agile movement, many have moved to a more collaborative environment and included testers and developers in the same team, or even the developers doing some level of testing. But we want to take this in general in the industry to higher levels, more of a team collaborative approach to this. And level 3 then, we are fully aware that testing can only show the presence of failures, but of course it can help us then build confidence in the quality. So, but there's always going to be some risk left, right? We cannot be sure that we cannot prove for any complex piece of software that all of it is correct. So it's about trading off. What kind of remaining risk do we have? We want that to be small, and the consequences of the remaining bugs or faults should be unimportant or not sort of critical for the operation of the system. But of course, this is a trade-off. So depending on how much we do in testing and quality work, the risks may still be high, and the consequences then of failures can be catastrophic. So the level 3, you have more of a collaboration. So testers and developer cooperate or are even the same people to in total reduce the risk. But this is a whole different level of maturity than you see in many companies still. But of course, there are increasingly more and more companies working like that. On level 4, kind of a level we aspire to, then it permeates all of the company, and it's a mental discipline to increase and build and assure quality software, right? And then we know that testing is not the only way. It's one way to increase quality. So we want to use other techniques in our toolbox to also help reduce the risk and increase the total quality throughout the development of software. So here in this in organizations on this mature level of level 4, test engineers can become technical leaders of the project as a whole even, and the primary responsibility is to measure and improve quality. And this expertise should go hand in hand with development and design expertise so that you get a good whole there. But this is the main thing missing often, because in order to collaborate, you need to trust each other, right? So as long as you see one of these activities as less important in any way, it's very hard to build a trust to get to a level 4 sort of collaborative mental discipline throughout development. And this is more in mature engineering disciplines. So in some of them, this is permeates all of things. So even when you develop or design an electronic component, for example, it's included there. Often it's inbuilt in CPUs, for example. That there are specific ports or ways of also testing the internals of the component, for example. When we talk about different levels, the classic model, process model for different levels of testing is a V model like this. This is from 2000, but it's much older than this. And the idea with a V model is that on the bottom, at the base of the V, you have the coding, so the development of the actual source code. Before that, you have steps where you go from abstract requirements, talking to the customer, analyzing needs, writing down and specifying what the software needs to do, then design on a high level, design on a detail level, coding, and then on the right in the V model, you will see different levels of testing that then corresponds to previous activities. So unit testing aims to ensure and weed out problems with detailed design. So it's on a low level components, typically a function, maybe on a class level, so a few functions as a whole is unit tested. But then on integration, you're now connecting multiple functions and multiple classes together to achieve some sub-goal, which is important in the architecture and the general design. And then you go to system testing, which then aims to show that the requirements, that is what is in the specification, is actually how the system behaves. And then acceptance test is where you involve the end user or some kind of proxy for the actual users, real or proxy for the actual users, and then you compare to what are the actual requirements, what are the actual needs of these end users. So the typical view when people present this V model is to say that this is sort of an abstract process model. It's not how many companies work today, and that's often true. But it's still a model that some companies today use, especially in embedded systems and in safety critical software. And of course, in practice, you cannot have a simple water flow like this, right? So not everything is going to be ordered in chronological in time like this. So often you need iterations. But companies still can sort of structure the way they work with verification and validation and testing in this way. And I had a master thesis a few years back in 2016, where we actually looked at a safety critical systems company, Scania in Södertälje in Sweden. We looked at their verification strategy, how they test the trucks. And actually here is a process view which was still active in many of their projects at the time. And you can see here it's of course more complex, there are many more levels, there are many more roles and responsibilities involved, but very interestingly you see a basic V model shape. Of course, they iterate, they nowadays work in agile teams and whatnot, but they still have an overview and process organization which is based on many levels like this. And of course, you see different terms and so on, but you can see the same ideas in here. So it's an interesting thesis, and it's also interesting for you maybe if you're going to do a master thesis here next year or so. It's one type of thing. So she actually helped them out there looking at what kind of ways can we automate more in this process for Scania. But the classical view here on the levels is that unit tests typically can be done by the developer or programmer themselves. So on a low level, you're going to write executable tests in some kind of framework like JUnit or CUnit, depending on what kind of languages you work with. There are many different implementations of unit testing frameworks. Developers on the unit level can also use automatic static analysis tools for verification, like checking that code standards are followed, that there's enough code comments, that variable names are used in the right way, indentation, and so on. And on the unit level, you can also do manual code inspection, so actually reading through the source code on the unit level, because this is hard to do for large subsystems. Then you have to divide up and do it between you, right? Integration testing level is about having test cases that ensure how do classes or modules of the system interact. So you're not looking at the level of the full system behavior, but you're looking at, for example, that the component interfacing with the database can work with the, say, statistics class or component, so that you can get the data and calculate the right statistics, right? So there's an interaction going on the integration testing level. You're not just testing that you can get data from the database. You're just not testing that the statistics component can calculate basic statistics. You're testing how they interact, right? Integrate. And then system test. This can be very often, many companies do still manual system testing. So you have manuals written for test cases to be done, or you do more explorative testing where you actually try to break the system. But increasingly, also system test cases are scripted. So you write complex, often longer tests that can be run automatically and test that the whole system behaves on an external behavioral level correctly. And then acceptance test is often manual, because you need to sit with some kind of representative for the customer or end user and manually test the software. So for example, I mentioned that Saab and the air traffic control software department, they actually, for acceptance testing, they have different levels of acceptance testing, but so they have like internal acceptance test, then they have former air traffic control tower leaders, people who worked in the air traffic control that are now working with Saab. So internally, they do acceptance testing, right, based on their experience from the work, from the field. But then also they do customer acceptance tests and different levels. Either they take the customers into Saab's site and facilities here in Gothenburg, and they actually run tests there. And then the highest level is with the customer in the customer's control tower in an airport. Of course, model-based testing doesn't really belong in a specific level here. If we look at unit, integration, system, and acceptance test, in theory, you could do model-based testing on all of these levels. So it needs a model, and you can do model-based testing on all of these different levels. So we will come back to that, what that can look at different levels. But that's a different sort of dimension here in looking at testing levels and types of testing techniques. One way to also look at this is like a testing pyramid. So this is an ideal world of the world, And you can read about this in the STTP book online that I also linked to in the module on Canvas. And the idea of a testing pyramid, so this is an idea, right? And the idea is that we need to do a lot of unit testing because then we can trust the units that they work. Then we can integrate them. So we do a little bit less of integration testing. When we know that different subsystems have been integrated well, we can do system testing of the specification. And then in the end, we run a few manual tests because they are costly. We need to have many people involved, take the customer to us and so on. And basically this means that you get more realism the higher you come, right? Because it's more and more like actual using the software, but it's also more complex. So when you find a problem on a higher level, it can be harder to trace it back and find the actual fault, the actual defect in the software to fix it. And there are many other trade-offs. And actually, in reality, this is a question for many companies. How wide should the pyramid look? Should it actually be a pyramid? Should it be, some companies say, no, we do more of system testing because then we don't need to do as much unit testing. And there are different sort of trade-offs involved here. And there is no good general answer to this, right? It could be the case that with very extensive system testing, that could be a cost-effective way, or it could be more like a pyramid, that if you do a lot of unit testing, you wouldn't need as much system testing. There's fairly little research on this, unfortunately, because it's a key question for many companies. Okay, so we're going to talk more about two main different testing techniques, and they can be seen as white box and black box testing. So black box basically views the system as a whole, or the unit, or an integration test, a collection of units. They view them as a black box. So we are looking at the software not internally, how it's designed, how the code is written. We look at it from the outside. We look at, based on what should this piece of the system or the software should do, how is it actually, how are we going to ensure that it does what it should do? So this is selection of test cases, creation of test cases based on often a specification or based on our experience of what should be happening for this type of module and unit. So we don't look inside the box, so it's black box. We pretend that we couldn't even access the software, and we look at it from the interface, from what it should be doing. So this has to be determined and based on some kind of specification. It can be explicit, so the specification could be written down in detail. What should happen when we do this? What should happen when we do this? Or it can be sort of modeled, so there's some kind of function that says what should happen if we give this input and so on. Or it can be more implicit, so it's left for cost efficiency reasons or other reasons. We don't really write down in all details. We kind of assume that the testers or developers will understand what we expect from the system in this concern, so they can write good test cases from the outside based on that concern. So the specification can be in different levels of degrees of detail, from very undetailed implicit to very detailed and formal, but the key thing is that in black box testing we don't look into the box. The opposite for white box testing. Here we look exactly into the box. So it's not black box, it's white box. We're looking into it and we're basing our test cases on covering or doing smart test cases based on knowing the code, based on knowing the structure of the case, of the software. So we still need to have a specification. So white box testing still needs a specification, because otherwise we cannot be sure that we get the response that we want, but we select the test cases based on the code and system structure. So yes, so a little bit more white box, also called structural testing, This is what we will give examples of in the coming videos and modules. Test cases are selected so that the program is executed systematically. So we try to somehow cover what's inside the software that we're testing. So the reference is the source code, or can be also detailed designs or designs of the source code, but majority of these techniques focus on the source code. And we build up some view of that source code, and we try to cover it in different ways. So the completeness of our testing, of our white box structural testing, is based on the structure. So how well do we cover the structure of the system? So if we look at one example of structural testing called statement coverage. So the goal is to cover all the lines of code or all the statements in the source code. Then we select test cases so that we cover every line, and we can measure how much we have currently covered of this type of structure by running 10 test cases, say, the one we've selected so far. We look at and we see, okay, we've now covered 8 of the lines of the 10 lines of this piece of code, right? So our statement coverage currently is 80%, right? We've covered 8 out of 10. So in that case, it will be 80%. And a goal in some standards of testing is to reach 100% statement coverage. But so you can select test inputs and which test cases to run in order to increase the structural coverage, like statement, and there are other types of structural coverage. But to know whether the actual behavior is correct, you still need sort of a black box understanding, even when doing white box. So you need an oracle, something that tells you, was this answer correct or not? So this is a slightly different here. To derive the test case, to create the test case in white box structural testing, you don't need to know what the expected answer is. But then to make it a complete test case, you need to add this oracle information. Is what the software is currently giving as output correct according to the specification or not? Yeah, and commonly how this is done, we will go into more details next time, but commonly we create some model or some structure from looking at the source code itself, and then we try to cover all parts of this code. So we're going to go into more details on this in the next video. To give an overview, so in the set of techniques called dynamic techniques and verification techniques, where we have testing techniques included, the structure-based white box testing techniques you need to know at least these 5. So there can be more, but these ones are well known. So statement coverage, decision coverage, condition coverage, path coverage, and data flow coverage. And in the coming videos and modules, we'll go through a few of them in more detail. So this was a little bit longer, but I also got the feedback from the Q&A last week that it was fine, so we can see where we end up in if you want me to split them further. But in the coming videos, we'll go more into details about different white box structural testing techniques.